rather than just staring at each other for the next 3 minutes. Let's do some math. Heavenly Father, we thank you for this day. Again, I thank you for this class and this opportunity we have to meet and study your creation once more, Lord. In your name I pray, Lord Jesus. Amen. All right, so first isomorphism theorem, linear algebra. I should prove this thing for you guys, right? So let's work on that. Let me restate it again. So here's the theorem. If T is a linear transformation from a vector space V to a vector space U, and W is the kernel of the map, has quotient map. Sorry. You're not late. I just started early. Pi of x, x plus w. So it's the quotient map, right? We just map x to its coset by w. Then the mapping t bar, which is a mapping from the quotient space of v by w, right, to u, defined implicitly by t bar composed with pi equals to t is an injection in particular t bar of x plus kernel t equals to t of x for all x plus kernel t in v by w. Moreover, v mod the kernel of t is isomorphic to the range t of v. All right, this is the so-called first isomorphism theorem. All right, so there's a few things to consider here. We need to show that, like, this mapping t bar is actually like well defined, you know. So let's see here. Notice that t of x, let's see here, t of x is an element of u, right, for each x and v. Hence, t bar is into u. What I'm saying here is, so if this defines t bar, right, the output of t bar is given by t of x, right? And since t of x is in u, that shows you it's into. Now into u, we don't even usually think about that much. But whenever I write a function, you know, going from a to b, having f of x is actually an element of b, this is what we mean by into. Right? That's a separate question from, is it single valued? Right? That's the next thing we should think about. Is t bar single valued? So suppose that we had x plus, x plus kernel t equals to y plus kernel t, right? Then that means that y minus x is an element of what? It has to be an element of kernel t by what we talked about last class, right? Two cosets are equal if and only if their difference is in the subspace. All right. Note. All right. So then t bar of x plus kernel t is equal to, well, t of x and so that's equal to, sorry, my brain is not, we can write that as, I'm trying to show my work here, t of x plus, let's say, t of 0, right? Which is t of x plus y minus x, right? Good grief. I can do that because y minus x is in the kernel, right? But then when I use additivity here, I get what? X plus y minus x, which is equal to t of y, right? Which would be t bar of y plus kernel t. So this calculation shows what? It shows that t bar is well defined. Hence, t bar is single valued. Like in print, yes?
How did you get the t y minus x from t0?
Well, right here, this means that t of y minus x is equal to 0. That's the kernel, definition of the kernel. Good question, yeah. So what I've shown here is that the output of t bar is independent of our choice of representative. Whether we feed it x plus kernel t or we feed it y plus kernel t, x and y being both representatives for the same coset, the output is the same, right? This is a single valued map. Okay, so next we need to show that t bar is a linear transformation. All right, so let's do that. So t bar goes from v by w to u again. Is it linear? So what do we have to look at? A linear combination, right? So let's do that. We should look at t bar of, let's say, c times x plus w plus y plus w, right? So can you guys, how do we add in the quotient space? How do we add those cosets? What was our definition? You guys remember? We scalar multiply the representative, right? So we get like cx plus y plus w, right? That was our definition of scalar multiplication and addition in v by w. And okay, so then as we've defined this is t of cx plus y, right? That implicitly defines t bar. It's annoying, but that's what we have to work with, right? And then, but t is linear. So this is c times t of x plus t of y, right? And then we once more use the implicit definition of t bar to switch this back to like c times, t bar of x plus w plus t bar of y plus w, right? Thus, t bar is an element of the linear transformations from the quotient space of v by w to u, because we've just showed it's additive and homogeneous. It's linear, all right? What remains then is to show that it's injective, right? We should show t bar is injective. How do we do that? What's our go-to, you know, what's our go-to trick for that? We need to show that the kernel, right, of t bar is just equal to like 0, right? If we could show that, we have a theorem, right? A linear transformation is injective if and only if its kernel is 0, right? What is 0? I mean, this is, by the way, equal to W, as, you know, the set just containing W, you know, as a subset of V by W, right? The 0 for the quotient space of V by W is equal to 0 plus W, which as a set is just equal to W. Am I clear? That's what we're hoping to show. That's the only thing that maps to. Anyway, that's 0 in V by W. Okay, so watch. Oh, wonderful. Wait a minute. Oh, man. And I didn't even I did the other way. There's two ways to check one-to-one, right? The one is like this. The other way is just to set their values equal and see what happens. I've done the other thing in the notes, but we could try to do this, right? So, all right, let's try it. All right, so we've got x plus w, an element of kernel t bar. What's that mean? T bar of x plus w, which is, by the way, equal to t of x, is equal to what? 0, right? Okay, great. What does that say about x? X is an element of what? X maps to 0. X is where? If you guys don't know what the kernel means, like, this is not going to work. We must know what the kernel means. Kernel is the set of all points which map to 0. So that, you know, this means x is in the kernel of t, though, right? Which we call w, right? Which means what? That x plus w is just actually equal to w, which implies that the kernel of t bar is just 0. Therefore, thus t bar is 1-to-1. Now, in my notes, I just I used the direct argument from the definition of 1-to-1. I checked t bar of x plus w equal to t bar of y plus w, and I show that then it's necessarily the case that y bar, assuming that y minus x is in the kernel. So, like, if you don't like this, if this argument doesn't make sense to you, look at the notes. There's a different one there. Okay. Okay, so we're almost done. We've got that it's an injection, right? What else? We're supposed to show that the mod the kernel is isomorphic to t of v, right? So the claim is that v mod the kernel of t is isomorphic to t of v, right? So here, just one more step, right? Like, what we're going to do is we're going to define yet another map, right? Which I think I've called t prime in the notes. So t prime let T prime be a mapping from V mod W to T of V by T bar, oh, my bad, T prime of X plus W equal to T bar of X. See that? In other words, what I'm doing is I'm just taking the codomain of T bar and I'm shrinking it down to the range of T, right? So, you know, T prime is injective since T bar is injective, right? Like changing the codomain of a map doesn't stop it from being injective if it's already injective. Is this onto? It's kind of dumb, but like let Z be an element of T of V, then what? Z is equal to T of X, right? For some X in V, right, by definition. And T prime of what is equal to Z? It's got to be a coset, right? Oh, this is equal to, right? Yeah. Oh, my bad. But you're right. But this was supposed to be X plus W here, right? T bar takes in cosets for inputs. Yeah, that was a typo right there. But you said X plus W, and I believe you are correct. Right. Because this would be T of X, which is Z. Therefore, T prime is onto. Therefore, T prime is isomorphism. And this is the first isomorphism theorem. Now you might wonder, if there's a first, is there a second? Is there a third? How many of them are there? Care to guess? Sadness. I think we're going to make it though. So there are, in Dummett and Foote anyway, which is the sort of like the most popular, I would say, abstract algebra book of our current, of your generation, perhaps the generation before yours. Dummett and Foote's abstract algebra has 4 isomorphism theorems. The first, the second, the third, and the fourth isomorphism theorem is known as the lattice isomorphism theorem, which concerns like a whole family of isomorphisms all at once in terms of some graph. I don't understand the lattice isomorphism theorem that well, but my brother tells me if you really understood it, you can prove everything with it. But it's kind of like, it's a lot to understand. So mostly we use the first isomorphism theorem. That's more often than not what gets used, you know. Any questions? So like a good example of this would be something like, you know, you can have a vector space, which is the direct sum of 2 subspaces, right? Then you could define, you know, T of x1 plus x2 equal to, say, x1, right? This is like the projection to W1, right? if you did this, what's the kernel of t? And here I'm using the usual notation, like, here. Okay? Remember we proved that there's a unique x1 and x2 if it's the internal direct sum. So given that discussion, this x1 plus x2, there's a, we can basically kill off the parts in x2. So if you think about this, the kernel is going to be, x1 plus x2 such that what? Such that x1 is equal to 0, I think, right? Because t of x1 plus x2 is just x1, so if we set that equal to 0, well, that just gives us, t of x1 plus x2. This is that, right? But think about that for a second. That's just x2, right? So if you can forgive me using notation a fair amount here, if we sort through it, then that's just W2, right? Like the kernel for this map is just W2. And so what does the first isomorphism theorem say? The first isomorphism theorem here says that W1 direct sum W2 mod the kernel, which is W2, is isomorphic to what? T of V, right? What is the range? It's just W1, right? Which is kind of satisfying, right? Like, you kind of cancel the W2s and you're left with W1, like that. So. Yep. Anyway, there are tons of applications of the first isomorphism theorem. I showed you guys another one last time, right? Like if we look at that symmetrizing map, the kernel, we get, like matrices mod, symmetric matrices gives you anti-symmetric matrices, all that. So there's tons of examples like that. Another good example that'd probably be healthy for me to talk about is the derivative. So oopsie. Example 2. How about the derivative, which is a mapping from, let's say, polynomials to polynomials. Here, P, I just mean, polynomials in X, let's say. So, we have F maps to, so like D of F of X is just equal to df dx, right? I mean, this is an example, right? You've spent some time studying this example, I think, right? Like Calculus 1 is mostly about this, right? What's the kernel of the derivative map? First of all, is it a linear transformation? I mean, yes, right? The derivative is linear. What's the kernel of the differentiation map? So we're talking about F. And we're talking about the kernel with respect to the polynomial ring, right? I mean, polynomials as a vector space. I don't know, I said that ring word. I don't know what it's talking about. So P such that df dx equals to 0. So what is that? All right. You guys are... So how about just constants, right? I mean, technically constant functions, if you like to think of it that way, but just the constant polynomials have derivative 0, right? So then we have that d, you know, d bar, right, that goes from p mod the kernel of d, right, over to polynomials, again, is injective, right? So how does that go here? We got like t bar, d bar, acting on, what is it, like, you know, the coset of f of x, right, is equal to what? I'm using the notation I did last time, right? Like f of x is equal to f of x plus, in our current context, kernel d. That's my w. So definition, just d f of x, right? So df dx, yeah? But we know the derivative is not injective, right? Like, I could have that this is equal to dg dx, right? Which would be d bar of g of x. Well, I mean, my question is that a problem? Or is this all consistent? Like, what does it take for two derivatives to be equal, the two functions? That means they're what? F of x minus g of x is equal to what? Just a constant. So what does that say? Oh, that says that actually this means then that the equivalence class of f of x is equal to the equivalence class of g of x. I mean, the coset of f of x and the coset of g of x. And yeah. So what is this explicitly? It's f of x plus a constant, right? To be clear. So what's the, is there an inverse to the derivative? Can we find the inverse map? So does d bar inverse a mapping from p back to, you know, p mod kernel d exist? Right? I think it does, right? So like d bar inverse of, let's say, you know, a0 plus a1x plus dot 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 plus an x to the n. I think you guys know what it is. It's what? Right. A naught x plus 1/2 a1x squared plus dot 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 plus an over n plus 1 x to the n plus 1, right? Notice that I've used the brackets there. What is that, though? As a set, it's constant plus, I mean, we can write it more, you know, constant plus a0x plus 1/2 a1x squared. There's probably a better notation for this, right? In other words, what I'm saying is that d bar inverse of f of x is just equal to the integral of f of x dx, right? And of course, you guys know the derivative of the integral of f of x dx is equal to f of x, right? It's not really true, though, that the integral is the inverse function of the derivative unless we're working not with just functions, but with equivalence classes of functions. Do you guys see why that is? Like, if I tried to invert, you know, here's the thing. d dx, right, would take x squared to what? To 2x, right? But if I undifferentiate, I can get back to x squared, right? But I could also get back to, x squared plus 1, or 2, or 3. And if I can't pin that down, that's not single valued. It's not an inverse, right? So there's two ways to go about this. The one is to make an ad hoc choice to pin it down to a specific choice of antiderivative, right? But I think a more responsible thing to say is that the inverse to the derivative is the indefinite integral, because the derivative is only invertible if we don't work with functions, but we work with equivalence classes of functions. Otherwise, the derivative is not injective, right? So like this whole thing here, if I have two derivatives are equal, it means that they differ by a constant, right? So the derivative is not injective. But if we replace the derivative with the derivative on equivalence classes of functions that differ by a constant, well, then that's an injective function and we can invert it. And the inverse to that is the indefinite integral. Because that's why we have to add a constant. We have to add a constant because we're not working with a single function. We're working with a whole equivalence class of function, a whole coset of functions. Anyway, I shut up. So that's all I got to say about that at the moment. This can, of course, be leveled up to what's the word? Differential equations. Like in differential equations, there's a similar story. You can talk about the homogeneous, you talk about things like mod the homogeneous solution or something. So, but I think I'm going to move along here at the moment. I want to talk to you guys about dual space and double dual space. So that's something new. So we're the business I'm just now starting here. It all goes together, like the dual space, and what we'll soon be talking about, bilinear forms and so forth. These things all kind of go together. So I'm going to focus here on dual space at the moment. We'll try to give you the basics. Man, this marker's trash. But I can't throw it out yet because it's new. But I want to throw it out. It keeps wasting my time. Dual space. What is dual space? Another trash marker. Get out of here. So the dual space, given a vector space V over F, a field, we define V dual, V upper star here, to be the linear transformations from V to the field. So I'm going to focus on the case that the dimension of V is equal to n. All right, I'm going to focus on the finite dimensional case in here. The discussion of dual space in the infinite dimensional, infinite dimensional case, there's a lot to say there. And it turns out that like the concept of dual space, it's a little bit too wild in the context of infinite dimensional space. You have to add additional terms and conditions. Like the problem of functional analysis, they don't just look at linear functionals. They look at so-called bounded linear functionals it turns out that the bounded linear functionals are the ones which are actually continuous. That is to say, you can have linear functions which are not continuous in the infinite dimensional category. So that's a problem for a later course. If you guys go on and take functional analysis in graduate school, you'll learn about that, all right? But I wouldn't ask you about that in here. So we're going to stick in the finite dimensional category, in which case, look, we already have lots of tools at our disposal. What's the dimension of V dual? Side question. You've got the dimension of V equals to n. You've got the dimension of W equals to m. What's the dimension of the linear transformations from V to W? Anybody? Nobody? It's the same as the dimension of Fmn, because there's a natural isomorphism from this to that, right? The isomorphism is, oopsies, it's like this, right? Psi of t is just the matrix of t, beta gamma for, you know, V equals to the span of beta, W equals the span of gamma. I mean, that's an isomorphism. Linear transformation, one-to-one correspondence with its matrix with respect to a given choice of bases, yeah? So the dimension is just m times n, right? M times n. In this context over here, okay? So that's just a reminder, things we learned earlier. How about this, though? What's the dimension of F? The reals are a what dimensional real vector space? This is not hard, yes? No, not like the reals over the rationals or something nefarious like that. I'm asking, what's the dimension of the reals over the reals? No. It's just one dimensional. One dimensional. Why? Because the reals are equal to c times 1, such that c is a real number, which is to say that they're the span of 1. So the dimension of the real numbers as a real vector space is just 1. So here we're going from an n-dimensional space to a one-dimensional space. So the dimension of V dual is n times 1, also known as n. So what does this all mean? Let me ask a loaded question. Well, is V isomorphic to V dual? They're two vectors, finite dimensional vector spaces of the same dimension, right? So yes, they're isomorphic. That's a theorem we have. Theorem. If V1 and V2 over F have same dimension, then V1 is isomorphic to V2. That is true, in fact. Right? I mean, if they have the same dimension, you can define an isomorphism from V1 to V2 by mapping the basis for V1 to the basis for V2 and extending linearly. That will define an isomorphism. We talked about this. So anyway, two vector spaces of finite dimension are, in fact, isomorphic, if and only if they have the same dimension. So it's simple as that in finite dimensions. So yes, V is isomorphic to V dual. This is true. And then there's also something called, what do you think about the double dual? So V double dual, the dual of the dual, right? This would be the linear transformations from V dual to the field. This would be the so-called double dual, right? So this, again, we would have that the dual space is isomorphic to the double dual space, right? By the same argument, basically. But you see that, of course, then that's also isomorphic to the vector space itself. So we have these natural isomorphisms of the vector space and its dual space, and in fact, its double dual space. The question then is, what are the isomorphisms, right? Like, this is great. We can argue by dimension that there's an isomorphism, but like, what is the isomorphism? Yeah? And like, is there just one isomorphism? I mean, probably not, right? There probably is like infinitely many isomorphisms possible. Could be, right? Could be. But can we understand one of them? So like, let's see here, example 3 perhaps. Let's see here. Let's keep it real for a second here, right? Alpha, a mapping from Rn to R, right? Okay, so like alpha of x is equal to, this, good grief, the sum, alpha of the sum. We can build x from what? I equals 1 to n of x sub I, e sub I. And so we're assuming that alpha is in the dual space, right? Which is to say that it's a linear map, right? So, okay, great. Then I can pull the sum out, yeah? And I can pull the constants x sub I out. And then I have alpha of ei here, like that. So, so I could write this actually as like alpha vector dot x, right? Just to invent a notation. What do I mean by alpha vector? I simply mean, look at this. This is the formula for the dot product, right? But here, alpha vector is equal to like, alpha of E1, alpha of E2, alpha of En, right? Although I suppose I could just, be less weird about this and say, well, it's the standard matrix of alpha, right? Times x. That is something we have a notation for, right? This is the linear transformation from Rn to R. So how big is the standard matrix? I don't need to invent that vector thing. We can just do this, right? What? That's a what? One row, right? 1 by n. So let me propose an isomorphism. I'm pretty sure we can build an isomorphism from, let's say, Rn dual to Rn via what? Let's say psi of alpha, right? Equal to what? I'd like to just put the standard matrix of alpha here, right? But I can't quite do that, can I? Why not? It's the wrong size, right? We need a column vector, but that's a row vector. That's easy to fix, though, right? Transpose this thing. Where did that come from? Well, I just did this calculation, and it showed to me that every alpha corresponds to simply multiplication by the, this, which of course you could also write as, this is kind of weird, but I could write this as alpha transpose dot x, right? I mean, my alpha vector actually, this in retrospect, this was alpha transpose, right? Okay. So sometimes people will say something like, the dual space of column vectors is just row vectors. And what they're talking about is basically this calculation, right? Every dual vector, a dual vector is an element of the dual space, all right? A dual vector is a linear transformation of vectors to the fields. And any dual vector on Rn can be implemented simply as the dot product with essentially a row vector. Okay, anyway. Okay, so definition. Man, I tell you what, this marker, this is like the fourth time today this has done this to me. I'll leave it for someone else. I won't throw it out, but it's going to just go down to the place of no man's land. Now, if you look at what we just did for the dual space, this was really anchored to the concept of the Cartesian coordinate system, right? There's a funny thing about the double dual spaces. There exists a so-called canonical isomorphism for V double dual. And so like if you define eval x as a mapping from say V dual to the field. So what do you think I mean by this? What's eval x? Evaluate, right? How would you define eval x acting on a dual vector? What's that going to be equal to? Yeah? How about this? Alpha of x. Right, this is for any x in the vector space. We can define evaluation at x. So this is for any alpha in the dual space to V. Remember, dual space vectors are themselves, they eat vectors and they output numbers. All right? Now, is eval x a linear transformation? Like if we do eval x on like C alpha plus beta, what happens? We get C alpha plus beta on x, which is C alpha of x plus beta of x by definition of addition of linear transformations. We add them pointwise. And then that, by definition, is C eval x of alpha plus eval x of beta. So thus, eval x is in fact what? A linear transformation from V dual to the field. And what does that mean? In fact, eval x is an example of what I was just introducing here a second ago, namely a double dual vector. Eval x is a double dual vector. And my claim to you guys is that, in fact, this suggests a natural isomorphism of V to the double dual. So, like, I can just define psi from V to V double dual. And if I say psi of x is equal to eval x, that is in fact a isomorphism. Like, so, I mean, to check on that, it's a little bit fussy, but like C of x plus, so if we do like C alpha plus beta, right? Oh, I'm sorry. My bad. I got to do like Cx plus y here, right? But then this thing is fussy. Is to understand that, I really have to let it act on, like, oh, I think I'm out of time anyway, but I think I have to let that act on alpha. Yeah. So eval Cx plus y on alpha is alpha of Cx plus y is C alpha of x plus alpha of y is C psi of x acting on alpha plus psi of y acting on alpha, which, by the way, is C psi of x plus psi of y, all acting on alpha. And since this holds for all alpha, therefore, psi of Cx plus y is equal to C psi of x plus psi of y. So thus, psi is in fact a linear map. And you can prove that, in fact, it's an isomorphism. Did I lose my double? Where did my... I thought I wrote 2 stars there. I'm sorry, guys. This was supposed to be star there. What's wrong with me? Good grief. I mean, I've proved that eval x is, in fact, such a thing, that it's a double dual vector by that over there, I think. Anyway, all I'm telling you guys is that there's this sneaky way of replacing a vector with a double dual vector, and all that amounts to is, like, the notation that I use other places is just eval x is like x hat. So if you have like x hat acting on alpha, that just amounts to alpha acting on x. So this is like typically how the double dual isomorphism is used. All right, anyway, I will shut up for today. Now that I have thoroughly confused you, seems like a good place to stop.